This is Usain Bolt, the record holder for the 100-meter dash and a victim of calculus. Derivatives are powerful since they can solve real-world problems with just simple tools. For instance, to find Bolt's acceleration in his world record run, all we would need is a video of his sprint and a map of the track he ran on. So, to learn what a derivative does, let's first make a graph. Using the map, let's split the track into 5 intervals of 20 meters each. Then we can plot Bolt's position on the track as a function of time. Doing this infinitely many times will produce a line. This graph now shows us where Usain Bolt was at each time. Getting back to the problem, using derivatives, we can find speed. Since velocity is speed with direction, and there's only one direction to consider, we can say velocity is speed. To get velocity, we need to divide position by time, or meters over seconds. Calculating each point's velocity will result in a new graph. This graph shows us how fast Bolt was traveling at each moment in time, instead of where he was at that moment in time. If you take the derivative one more time, we can find acceleration, or meters over seconds squared. This graph shows us how fast Bolt was speeding up or slowing down, instead of how fast he was traveling. So now we know that a derivative is simply just the tangential slope of a graph at a certain point. Although they are useful in physics, derivatives come from calculus. With certain rules memorized, based on the type of function, we can accurately figure out the new graph using derivatives. The new notation for a graph that is the derivative is noted as f prime, with a symbol like an apostrophe. Not all graphs can have a derivative, however. To have a derivative, the graph must be continuous and have a limit that is equal to the derivative.